Hello listeners, today we will be discussing about the classification of igneous rocks. Here is a brief outline of the talk. We have an introduction section followed by the classification based on chemical composition. We have silica percentage, we have silica saturation classification, alumina saturation classification, alkali lime index classification, and total alkali silica based classification. Rocks, as we know, are composed of minerals, and minerals in turn are made up of chemical elements. Hence, using the chemical composition for classification of igneous rocks is an ideal way of doing it. Chemical classification requires partial or complete compositional analysis of igneous rocks. A number of chemical classifications of igneous rocks have been devised, which we will be discussing in our lecture. Silica percentage. Shand and Holmes devised a method to classify igneous rocks based on the silica content present in the rock. There are 4 categories based on this. We have acid igneous rocks, which has silica percentage more than 66% in the rock. We have intermediate, which has 52 to 66 weight% silica in it. Then we have basic igneous rocks, which have 45 to 52% silica content in it, and we have ultra basic rock, which is less than 45% silica content. Here is an example of an acid igneous rock, rhyolite, which is being shown. These rocks have more than 66% silica content. They are also called as felsic or silicic rocks, and as common examples we can have granite and rhyolite. We have the intermediate igneous rocks. These rocks are having 52 to 66% silicon dioxide in them. Common examples include cyanite or diorite, trachyte and andesite. And here you can see an example, which is the andesite. We have the basic igneous rocks, which has a silica content varying between 45 to 52%. They are also called as mafic rocks. Common examples include gabbro and basalt, and you can see the gabbro hand specimen here. Then we have the ultra basic igneous rocks, which has a silica content less than 45%. They are also called as ultramafic rocks. These rocks are known to have high magnesium content. Common examples include dunite, peridotite, pyroxenite, and you can see the hand specimen of a pyroxenite. Here you can see the different rock types which crystallizes under these categories. We have acid igneous rock, the plutonic rock is granite, and the volcanic equivalent is rhyolite. For the intermediate rocks, which is varying from 66 to 52% silica, we have diorite as the intrusive rock and andesite as the extrusive rock. For basic rocks having silica content between 52 to 45, we have gabbro as the plutonic equivalent and basalt as the volcanic equivalent. Then we have the ultra basic rocks where we have peridotite as the intrusive rock and komatiite as the extrusive volcanic equivalent of it. Also here you can see the mineral compositions being shown against each of these varieties, where we have acid, intermediate, basic and ultra basic rocks, where you can see that acid rocks are known to have a certain proportion of amphibole, biotite, muscovite, potassium rich plagioclase feldspar. Then we have quartz and potassium feldspar, which is the dominating constituent in these rocks. Then we have the intermediate igneous rocks. We have amphibole as a mineral constituent, biotite, some amount of muscovite. Plagioclase feldspar is the dominant constituent in these rocks, and we have a certain proportion of quartz and very less proportion of potassium feldspar. Likewise, basic rocks, we have amphibole, some amount of olivine, then we have pyroxene and calcium-rich plagioclase as its constituent. For the ultramafic rocks, you can clearly see that we have olivine and pyroxenes as the major mineral constituents. Then we move on to the classification based on silica saturation. This was given by Shand in 1913 and it was revised by Holmes in 1917. Igneous rocks are divided into 3 groups based on the basis of free silica. We have silica oversaturated rock, which has more than 66% of silicon dioxide. Silica saturated, ranging between 52 and 66% silica content in the rock. and silica undersaturated, that is 45 to 52% of silica in these rocks. So here we have the classification, we have the group silica oversaturated, silica saturated and silica undersaturated. Silica content is being shown, which for silica oversaturated it is more than 66%. The rocks which crystallizes under this group is a granite, and here you can see a granitic rock. Then we have the silica saturated variety, where the silicon dioxide content varies between 52 to 66%. Common rock crystallizing under silica saturated category is diorite, and here is an example of diorite. Then we have this silica undersaturated rock, which has a silicon percentage of 45 to 52. Common rock type crystallizing under this is nepheline cyanide, and here is an example of a nepheline cyanide hand specimen. The next classification, which is the alumina saturation index based. After silica, alumina happens to be the most abundant oxide present in any igneous rock. Shan in 1943 devised classification based on alumina saturation index. There are three subtypes we have: paraluminous, metaaluminous and paralkaline, where we have these formulas where we have the A by C and K. These values have to be determined for doing this classification, where we have the ratio of A by C and K, which is the amount of alumina present divided by the total amount of calcium oxide, sodium oxide and potassium oxide calculated in mole percentage. Then we have the A by Nk value, which is the Al2O3 mole percent in the rock divided by the total Na2O plus K2O mole percent. So what are the paraluminous igneous rocks? These contains excess alumina then required for formation of feldspars. They can be chemically expressed as rocks which are having Al2O3 more than that of the sum of calcium oxide plus Na2O plus K2O in its chemical composition. The A by C and K value is more than 1, where I have already shown you that A stands for aluminium and C stands for CaO, N stands for Na2O and K stands for K2O. The minerals which are generally crystallizing in the paraluminous igneous rocks includes muscovite, corundum, kyanite should be present. Then we have the metaaluminous igneous rocks, where the molecular percentage of this category is expressed in the form where Al2O3 is less than that of combined value of CaO plus Na2O plus K2O, and Al2O3 is greater than combined value of Na2O plus K2O. As has been shown here, A by C and K should be less than 1 and A by Nk should be less than 1. This does not contain any alumina rich minerals. They lack alkali pyroxene and amphibole also in their composition and is quite common in igneous rocks. Then we have the paralkaline igneous rock. This group is alumina poor and oversaturated with alkalis. On a molecular basis, it is expressed as Al2O3 should be less than that of Na2O plus K2O. Here we have A by Nk, that is Al2O3 by Na2O plus K2O value is less than that of 1. Then we move on to the classification based on the alkali line index. In 1931, Peacock, a petrologist, examined suites of igneous rocks throughout the world, and he used this classification for a related series of igneous rocks using silicon dioxide content, Na2O, K2O and calcium oxide data. He plotted the calcium oxide versus silica and the Na2O plus K2O versus silica values. Commonly, it is seen that the CaO decreases and Na2O plus K2O increases with respect to silicon dioxide. So here is the diagram showing you on the x-axis we have the silica weight percentage, and on the y-axis we have a double y-axis. We have here on this side we have the calcium oxide weight percent, and here we have on the other side Na2O plus K2O weight percent. You can clearly see that the alkalis are seemingly increasing with increasing SiO2 content, and the line, that is the CaO, is decreasing with increasing silica content. And where these two lines intersect, this point is known as the Peacock index or alkali line index. Peacock used the value of silica where the two curves intersect, known as the Peacock index or the alkali line index, to divide the rock suits into the following categories. We have alkalic rock suit where Peacock index is less than 51. Then we have alkalic calcic rock suit where we have the Peacock index lying between 51 and 56. We have the calcic alkalic rock suit where the Peacock index is 56 to 61. And we have the calcic variety which is having a Peacock index more than 61. Then here we have the total alkali silica classification. Total alkali silica diagram happens to be the most popular chemical classification scheme given by Lee Bass and others in 1986. This uses major element chemistry to classify igneous rocks. A simple XY graph with the axis showing the silica percentage, weight percentage, and the y-axis showing total alkali silica, total alkali, that is Na2O plus K2O weight percentage, is used for this classification. And then also we have a boundary line which can separate the alkaline rocks from those of the subalkaline rocks. So here is the diagram of total alkali silica plot where you have the silica percentages varying from 35 to 75% weight percent in the x-axis. Then we have the Na2O plus K2O weight percent varying from 0 to 16 in the y-axis. Here you can see that basalt is having a composition. These lines which are being there, this divides the different chemical compositions and this defines where your basalt composition will be. You can have a basalt be lying between, having a silica percentage lying between 45 to 52% and have the Na2O plus K2O data varying from 0 to 4 or even more than 4. Anything which is lying within this field will classify to be a basalt. Likewise, if you have an andesite, it will have a silica percentage more than that of a basalt, and we have here around 52 to around 63 percentage. This is the field of andesite, and as you can clearly see, the silica field is quite constricted, but then you have a wider range of opportunity to change the Na2O plus K2O content. And rock lying here will also be an andesite which is having around 5 weight percent of Na2O plus K2O, and likewise a rock lying here as well with a 2 weight percent of Na2O plus K2O value will also classify to be an andesite. So these different fields have been marked. We have phonolite, tephrophonolite, phonotephrite, tephritic basanite, we have picrobasalt, basalt, basaltic andesite, andesite, andesite. So here is a line which is marked in dashed, which is classifying the rocks into two groups. We have the alkaline rocks and then we have the subalkaline rocks. So in summary, we have the classification of igneous rocks based on chemical composition. First one is the silica percentage, where we have acid igneous rock which is having silica percentage more than 66%. Then we have intermediate igneous rocks which is having silica percentage lying between 52 to 66%. Then we have the basic igneous rock where the silica percentages lies between 45 to 52%. And we have the ultra basic rock where we have the silica percentages lying having less than 45% of silica. Acid igneous rock example is that of granite. Then we have an intermediate, we can have andesite. For basic rock, we can have a basalt. For ultra basics, we can have dunite or peridotite. The classification based on silica saturation, we have silica oversaturated rock where the silica percentage is more than 66%. Then we have saturated rocks where we have silica percentages lying between 52 to 66%. Then we have undersaturated silica bearing rocks where the value of silica lies between 52 to 66%. Then we have the other way of classifying it is the alumina saturation we have paraluminous variety, metaaluminous variety, and paralkaline variety, which is based on the value of A by CNK and A by NK, where A by CNK is Al2O3 proportion by calcium oxide plus Na2O plus K2O mole proportion. And for A by Nk, we have Al2O3 divided by the sum of Na2O plus K2O in mole proportion. And that allows us to classify the rock into paraluminous, metaaluminous, and paralkaline variety. Likewise, we have alkali line index, which is based on the Peacock index, which is the intersection of the line two curves, that is the curve showing increase in the alkalis based on the with increasing SiO2, and the one where we show a depletion in calcium oxide based on the with increase in silicon dioxide, and that value, if it lies between less than 51, we call those rocks as alkalic. And if we have Peacock index lying between 51 to 56, we call that as alkali calcic. Then we have calcic alkali, where the Peacock index is between 56 to 61, and we have the calcic variety where the Peacock index is more than 61. And the last one is the total alkali versus silica plot, which is actually an XY graph with marked fields for each rock type. And we calculate the X value, which is happens to be the silicon dioxide weight percent. Then we have on the y-axis the Na2O plus K2O value in weight percent. And it also allows us to classify the alkaline and subalkaline rock types. In summary, I would also like to again reiterate that these are classifications which require us chemical analysis of the igneous rocks. Thank you for listening.